On problem 3, you're given clock times and you're given depth. For now, ignore the stuff in green. Comes at the end. And you're given that y is the vertical distance from the vertex to the data point, where the vertex is this point, and each of these is a data point. X is the horizontal distance from the vertex to the data point. Well, okay, what's y for this data point? Its distance from the vertex to the data point, which is from 30 to 100, that's 100. 30 to 130 is 100. What's the distance of the clock time here from the data point? Well, the difference is 749. Okay, so there are the y and x components that correspond to this data point. Now, the graphical picture is worth having. So here's a graph of depth versus clock time. Here's the vertex at 810.30. Here's your first data point at 6130. And we can see graphically that the distance from here to here, or the distance between these points, is 100 units of depth. And that in case would be 100 millimeters. And the horizontal distance is 749 seconds. From 61 to 810 is a difference of 749. Now, I'm suppressing the units just to deal with the numbers, but keep in mind that the distance of x, which is distance, the horizontal distance from our data point to the vertex, if we go from here to here, the horizontal distance is 749 seconds. The x are measured in seconds. The x values are measured in seconds. And the y values in millimeters, because all the vertical quantities, the vertical quantity is depth in millimeters. The vertical distance between 2 points will therefore be a change in depth, or a difference in depths in millimeters. Nobody got this y versus x thing. Pretty much everybody used this as y versus x, and the problem doesn't make a lot of sense if you use y versus x here. That's not what y is, that's not what x is. So anyhow, so whether it was just not reading carefully enough or not knowing what to do once you did read it, and that's perfectly plausible. It just didn't happen on anybody's test. Okay, so moving on from here though, we can easily graph y versus x. Right there are our numbers. Right here is a perfectly good graph. Now, when I made this graph, the y versus x values are depicted by points, and those points are labeled and they're in orange. 380 20 point, I think, was somewhere around here. Actually, more like over here, wasn't it? Okay, so there's a point, there's a point, there's a point, there's a point, and there's a point. Now, there's no reason these points are going to lie perfectly on a smooth curve. I've drawn them as if they do, but there's a good chance the curve is going to have to kind of split the difference in some of these points. Okay, well, and here are the coordinates of the points, and the coordinates match the coordinates that we have on the table. So that's all very straightforward. Okay, so let's see. We do this, we get this y versus x graph, and then we try to determine the factor by which y changes when x doubles. Okay, now that's where these marks come in. I've got a series of red marks here, each of which doubles the coordinate of the preceding one, or attempts to do so. And looking at these red marks, we project up and over to get the y coordinates. It looks like the y coordinate at least triples between here and here, and it may be pretty close to quadruples, fourples, between here and here. So it looks like, according to the red marks, the points that I've indicated by the red marks, y changes by a factor of maybe 3 or 4 when x doubles. And a question mark there because we don't get really consistent results from these 2 points and then from these 2 points. Okay, so I pick another point. Now I picked a point out here just to use as much of the graph as possible, and then I cut that in half, and I projected up to the graph and over, and I got this coordinate, and up here and over I got this coordinate. Had to extrapolate the graph a little bit. That's kind of a little bit dangerous, and we found that this was 1, 2, 3, 4, probably looks like about a factor of 5. Well, in fact, this graph, if done carefully and correctly, should be very close to fourpling whenever x doubles. So you pretty much have the fourpling graph, and we know that that's y equals ax squared. Okay, now we're going to take a point on the graph. I just picked my very favorite point on this graph, 550, 57. And I picked the point, and then I projected over here and estimated this to be 57, projected down, estimated to this to be about 550. So using y equals 57 when x equals 550, I substitute the 57 for y, the 550 for x. I get 57 equals a times 550 squared, so that a is 57 over 550 squared, which is pretty close to 0.00019. So that's the model that we get using this curve and this point on the curve. Our model is thus y equals 0.00019 x squared. And to check that, we use y equals 0.0019 x squared, and we plug these x values in, and we get the numbers indicated in red. Now these numbers are all higher than the number in red by somewhere usually between 5 and 10 units. So the model isn't great. It doesn't fit the data really well. There are ways to get much better models, but this is not too unreasonable a model. Okay, we could use it to get reasonable results. Okay, well, now what we want to do is we want to see how we can use this model to get ourselves a model for this curve. There's a clear and close relationship between this curve and this curve. Just a simple linear transformation. We've just changed the x and the y coordinates, but in a consistent way, so we should be able to transform this function back to get an equation for this curve. And the relationship between x and y is very clear. If you think about what we did to get these numbers, we took the 810 here, we took the 61 here and subtracted it from 810 to get the x distance. We then subtracted 136 from 810 to get the y distance, 674. And we did that in every case. So that x in every case is 810 minus this number being the clock time. So we can say x is 810 minus clock time. Now, how did we get the depth? Well, we subtracted the coordinate of the vertex from the depth. Now, here we subtracted from the coordinate of the vertex to get the x values. Here we're subtracting the coordinate of the vertex to get the y values. Why is that? Well, simply because all the clock times are less than what we have at the vertex. So in order to get a positive number, and the distance has to be a positive number, we have to subtract this from this. Why did we subtract this from this? Well, these numbers are all bigger than this. If we want to get this distance, we have to get a positive number. So we do the subtraction in what feels like the opposite direction. Okay, anyhow, 130 minus 30 gave us the 100, 110 minus 30 gave us the 80. And from that pattern, we see pretty clearly that y was depth minus 30. Now, if x is 810 minus clock time, y is depth minus 30, and y equals 0.0019x squared, you can't see it over there, it's off the screen now, but if y is 0.00019x squared, well, what's that give us? Well, y is depth minus 30, so let's replace y with depth minus 30. And x is 8:10 minus clock time, so let's replace x with 8:10 minus clock time. Okay? And, I kept everything else that was originally in orange, except that square probably should have been in orange to keep with my color scheme here. Color scheme isn't all that important, but it's maybe helpful to see where things are. Okay, so now the question then is, what we want depth as a function of clock time. So how do we get depth as a function of clock time? We solve for the depth. Now, solving for the depth is very straightforward. We just add 30 to both sides. Nothing to it. So we get depth is 0.00019 times 810 minus t quantity squared plus 30. Now, instead of clock time, I just wrote t. Okay, we understand that t now stands for the clock time. I don't want to use y for depth because we're using y for something else in this situation. And then I simply simplified this expression. Now, what's simple and what isn't? This is a very simple form, and in many senses this is the simplest form because you can read off the vertex of this graph. If you know just a little bit, if you know what you probably should know in algebra at this point, you know that this function is quadratic, and the graph of a quadratic is a parabola. So this is a parabola, and it has a vertex, and the vertex in this case, and I'm not going to go through all the details of that, but the vertex in this case is just easily read. The vertex occurs when this term is 0, that's when t equals 810, and the depth equals 30. Okay? So, if I expand this square, okay, and expand the square, you're just going to get t squared minus 2 times 810, that's minus 1620, plus 810 squared, t squared minus 1620t plus 810 squared, and multiply that by 0.00019, and then collect your terms. You're going to get 125 out of this thing when you multiply through by the 0.00019. You're going to add that to 30 to get to 155. It's very simple. You just do what it says, expand it, and express it in the standard form of a polynomial. So it's what we have here, or what we have here is a quadratic function. And you should either review or anticipate the graphing of quadratic functions. You, I think, should have seen it by the time you finish Algebra 2. And if not, then you certainly see it fairly early in a pre-calculus course. Now, if the process of the proceeding worked as it should, remember your model, which I've copied down here now, just copied from before. If we plug these values for t, these values here for t, into either of these functions, these are the numbers that we get. Okay, well, this number is 6 higher than this number, just like this number was 6 higher than this number. This number is 6 higher than this number, just like this, and so forth. The difference between this number and this number is always the same as the difference between this number and this number. And that's exactly as it has to be if we've correctly transformed this function back to these coordinates. And that's worth thinking about. I'm not going to elaborate on that. I'm going to simply say that we've taken this data, we've changed to y and x coordinates so that we could easily get a reasonable model. We got our model, and then we transformed back to these coordinates and plugged our numbers in, and they came out the same relative to the depths as these numbers did to the y's. If you continue your mathematics education through at least a couple of years of college, you'll see a lot of examples of transformations and how using transformations, as did in this case, making it easy to find a model, can simplify things greatly.